Chapter 9, Section 3, Inner Product. In this section, we explore what is inner product, what are the differences between dot product and inner product, and key properties of inner product. In the prior section, we already discussed dot product. The dot product is the inner product of vectors in Euclidean space, while the term inner product encompasses a broader concept, including vectors in spaces beyond Euclidean space, such as complex vector spaces. In short, inner product is a more general concept. All dot products are inner products, but not all inner products are dot products. Let's compare dot product and inner product. For two vectors u and v in Rn, the dot product is a specific type of inner product, defined in this way. This operation returns a scalar, not a vector. The inner product is a more general concept that extends beyond Rn. For example, in complex vector spaces, it is calculated by taking the complex conjugate of one of the vectors. Thus, while the dot product is a special case of an inner product in Euclidean space, the term inner product applies more broadly. In notation, dot product uses the centered dot symbol. Inner product uses angle brackets. In Euclidean space, the dot product and inner product are the same. As shown in these examples, for the vectors u and v, both in Euclidean space, the dot product and the inner product have the same scalar value, 32. Let's see an example of inner product in a complex vector space. For two complex vectors u and v in complex vector spaces, the inner product is defined in this way. That is, take the complex conjugate of the second vector's components before multiplying. Let's see the calculation process step by step. First, compute the complex conjugates of v. Next, multiply corresponding components. Then, add the results. This is the final answer. An inner product must satisfy the following three essential properties to be called an inner product: conjugate symmetry, linearity in the first argument, positive definiteness. These three properties are what to make an operation a true inner product. They enable us to go beyond simple multiplication and give the inner product a rich geometric meaning, enabling us to talk about length, angles, and orthogonality in abstract vector spaces. Let's explore these properties one by one. Conjugate symmetry means that swapping the order of the vectors gives us the complex conjugate of the original inner product. The horizontal bar above the expression on the right-hand side denotes the complex conjugate. The complex conjugate of a complex number z equal a plus bi is written as z bar equals a minus bi. It simply flips the sign of the imaginary part. In real vector spaces, there is no need to take the conjugate, so the property simplifies to this equation. This equation just says that the inner product is symmetric. This property is essential when working in complex vector spaces, where inner products can be complex numbers. For example, if the inner product of u and v equals 3 plus 2i, the inner product of v and u equals 3 minus 2i. This behavior distinguishes the complex inner product from the dot product used in real vector spaces, where no conjugation is necessary. Next, let's focus on another property. linearity in the first argument. This property can be expressed by this equation. This means that the inner product behaves linearly with respect to addition and scalar multiplication in the first argument. That is, taking the inner product after combining vectors is the same as combining the inner products individually. Intuitively, this is like the distributive property and scalar multiplication working nicely inside the inner product. This linearity applies only to the first argument. The second argument may have a different rule, so don't mix them up. Now, let's go on to the third property, positive definiteness. This property can be expressed in this way. It says the inner product of a vector with itself is always greater than or equal to 0. It is exactly 0 only when the vector itself is the 0 vector. This property is fundamental because it enables us to define concepts like length and distance between vectors. Let's wrap up. While the dot product is specific to Euclidean spaces, the inner product applies to a broader range of vector spaces, including complex vector spaces. This section covers three properties of an inner product: conjugate symmetry, linearity in the first argument, and positive definiteness. These properties ensure the mathematical soundness and geometric consistency of inner product spaces. Understanding inner products lays the groundwork for further topics in data science such as projections, orthogonalization, and dimensionality reduction. Thank you for watching. Please thumbs up and subscribe to my channel.